Well, hi everybody. I was hoping I wouldn't have to do this, but it seems like we keep missing classes, so I just want to make a short video here. I'll try to go somewhat quickly through my notes here, just the starting material, and just to tell you a little bit about how to use these, and also, well, mostly we're just introducing some definitions. All right, so to start with, my section 1.1, I talk a little bit about the history, a little bit about the brief history of math, and basically the point of this page and the next page and the page after that is just to give you a quick rundown of some of the events and people whose life's work led up to the construction of numbers, which sort of laid the groundwork for Newton and Leibniz to discover calculus. So I'll let you read those pages. I hope you get something interesting out of them. But let's start with the material, which really we'll be using. Now, the things I'm telling you about in this video, they're more about. It's really more informational than it is, let's say, about problem solving. So, really, I need to tell you guys about some language. All right. So, to start with, we do like to use sets. A set is a collection of elements. X is an element of S. We have a shorthand for that, X, element of S. This is a shorthand for X is an element of S. Or you could also read it X is in S. For example, R is the set of all real numbers, so when we say X is an element of R, that just means that X is a real number. Another important concept, and sorry, I don't have a color printer. This is green in my notes, right? I try to make the definitions green and theorems, and anyway, you can read about the color coding, whatever. So two sets are equal if and only if they have the same set of elements, all right? And for a set, we don't care about the ordering out of elements. So like the set ABC is the same as the set BAC, is the same as the set CAB. Now, if we were going to care about the ordering of elements, then these would be different. But if you want a set with which distinguishes between the order of elements, then you wouldn't want a set. You'd want a list. All right. We also have this notation called set builder, or sometimes it's called roster notation. S, the way this is read, is X such that X has this property P. So this is so-called set builder notation. We'll talk more about that. A set with no elements is called the empty set. We can either denote it by curly brackets with nothing in between them, or this empty set. When I write that by hand, the empty set symbol tends to look like this, all right, ish. Subset. We say S is a subset of T, and we denote it by that. If for each S in S, we can show S as an element of T. All right, that's the definition of subset. And we can also define union and intersection. So like the union of two sets is a new set, which is formed by taking all the elements in one and all the elements in the other and just put them together. So to say X is in the union is to say that X is in S, or S is in X is in T. The intersection, on the other hand, is the set of elements which are in both sets at once. So it's X such that X is an element of S and X is an element of T. And this right here, maybe you're less familiar with. This is called set difference. So S minus T is S that is in the set S, but it's not in T. All right, so set difference. So we do use some set theory here and there to try to explain things. So some common notations that we would like to know about and use as a point of reference. Natural numbers, I use and this is the natural numbers, like this. Integers, like that. And rational numbers, like that. All right. So natural numbers, like it says, 1, 2, 3. Integers are 1, 2, 3, but also, minus 1, minus 2, minus 3, and 0. And rational numbers are fractions formed by, quotients of integers. So if I was to put these three in if these are actually, I can put them as subsets, right? Like the natural numbers are a subset of the integers, and the integers are in fact a subset of the rational numbers. And if we were to continue, this is a subset of the real numbers. And by the real numbers are a subset of the complex numbers, all right? So there you go. There's some examples of subsets. But let's see here. So here's a quote-unquote in-class example. So I've left some little examples to fill out here and there in the notes, so let me do that. I'd really hope to do this with you in person, but oh well, it is what it is, right? So so we've got the set 1, 2, 3 and minus 1, 0, 1, and we're supposed to find the union and intersection, so I'll just go ahead and do it. So S union T. All right, so what I do when I do this kind of thing is I just write down the 1. S has got 1, 2, and 3, all right? And then T has got minus 1 and 0 as well. Now I don't need the 1 because I've already got it in there, so there's S union T. Now S intersection T would be everything, so the numbers which are in both. So 1 is in both, and 2 is only in S but not in T, and 3 is only in S but not in T, so the intersection just has the set containing 1. All right, so we found those two, and we're supposed to determine which of the natural numbers, the integers, or the rational numbers contains S union T as a subset. So these are not fractions, they're just integers, so this is definitely a subset of the integers. And by the way, that is a subset of the rational numbers. So in other words, the union of S and T is a subset of both the integers and the rational numbers, but it's also true that S union T is not a subset of the natural numbers. On the other hand, S intersection T is a subset of the natural numbers because the number 1 is a natural number. All right, so there's a kind of a silly exercise, but I've included some of these here and there just to try to help hopefully help you understand what union intersection mean if you didn't ever see it before. Although, I hope you've seen it before. Excuse me. Oof, goodness. All right, let me move along here. It shouldn't take us too long to get through this here. The Cartesian product is another thing we can do with sets. All right, so the Cartesian product is a set of ordered pairs. So the key property of an ordered pair xy is that if you have xy equal to a comma b, that's true only if both x is equal to a and y is equal to b. So that's how an ordered pair is constructed. That's how it works. If you have two sets, a and b, a cross b, or in other words, the Cartesian product of a and b is the set of ordered pairs where x is taken from a and y is taken from b. We also use the notation a cross a is a squared for a set of ordered pairs. Most typical use of that would be like R2, which is R cross R. It's a set of ordered pairs of real numbers. So we naturally associate the R2 with the xy plane, all right? And I usually just refer to it as R2. R2 is R cross R, all right? Now, I made this bunch of dots here to illustrate the Cartesian product of A and B. So like A has got numbers 1, 2, 3, 4, 5, and B's got 1, 2, 3. So A cross B has these, these dots right here. Boop, 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 doop, 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 doop. And if you could zoom in, you'd see that 1, 2, 3, 4, 5, and 1, 2, 3. So they're when you have two finite sets and you take their Cartesian product, the number of elements you get is just the product of the sizes. Like A cross B is the number of elements here is 3 times 5, which is 15. All right, so the next example here is the question is 1 comma 5 in A cross B? What about 5 comma 1? Let's think through that. 1 comma 5, is it in A cross B? What would that mean? We need 1 is an element of A, and we also need that 5 is an element of B, right? But one of those things is not true, right? That's, not true. So, therefore, 1, 5 is not an element of A cross B. Now, in terms of the Cartesian plane here, 1, 5 would be like up here-ish, right? So that point is, not in A cross B, which is pictured. Now, on the other hand, 5, 1, right, 5, 1, well, that point is 5 over 1 up. That's this point right here, right? So, yeah, 5, comma 1 is an element of A cross B. That is true. Yep, that is true. And that is true because 5 is an element of A, and 1 is an element of B, so it is in A cross B. All right, so that's Cartesian product. So I'm just going to keep going through here. This is mostly for your information, but these are definitions we need to know, because if I talk about an integer, you need to know what I'm talking about. If I talk about a real number, you need to know what I'm talking about. If I talk about a rational number, you need to know what I'm talking about. So here we go. So what are real numbers? Well, a real number we could construct from base principles, but that would really, well, you'd need to be a math major, and you'd probably need to take a course we don't offer. So I don't think we really have a course that fully develops the real numbers at the undergraduate level here. But rest assured that you can construct the real numbers from set theory and mathematics alone. There are ways to do that. So rest assured that they do exist. There are various ways to construct them. But however you construct them, everybody agrees that they have to have these properties. That's what makes them real numbers. So real numbers are defined by this set of axioms, all right? Real numbers are a set. They have an addition and a multiplication. The addition is commutative associative. It's got a 0. It's got additive inverses. The multiplication commutes. It's associative. There's something called the number 1. It multiplies by anything to give you back the anything. Every non-zero element has a multiplicative inverse. You have the distributive property, and this is interesting. So everything up to this point would also be true. Everything up to this point would also be true for like rational numbers, or even complex numbers, right? But part 10, axiom 10 here, would only be true for reals or for rational numbers. Also, this 10 is true for. But complex numbers don't have a nice ordering that respects the other, the addition and the multiplication of the field. Okay. So real numbers, all these nice algebraic properties, and they also have this trichotomy that either A is less than or equal to B, B is less than or equal to A, or A is equal to B. Oh, I'm sorry. Oh man, I'm not saying this right. Anyway, here's the axioms for a totally ordered field. If we have A is less than or equal to B and B is less than or equal to A, then we of course get A equals to B. You also have this transitive property, A less than B, B less than C implies A less than C. And I think I was thinking of totality. Totality, either you have A is less than or equal to B, or B is less than or equal to A. Another way to parse this would be either A is less than B, or B is less than A, or A is equal to B. That would be the trichotomy I think I was thinking about. My bad. And then axiom 11 is actually rather technical, truth be told. Least upper bound property. Every non-empty subset of the real numbers has an upper bound, has a least upper bound. This makes the real numbers what are called complete. They're the complete ordered field. And this completeness axiom is not true for rational numbers. We'll talk more about that when the time comes. But this axiom 11 is actually what makes a number of the more interesting theorems in Calculus 1 true. So it's kind of important. All right, anyway, so we I did just throw a new term in there, which is upper bound. What's an upper bound for a set? An upper bound for a set is a number m such that m is greater than s for every s in the set. All right, so that's like an upper bound. You could also talk about a lower bound. It would be a number which is less than every number in the set. And if it's bounded above and below, then the set is said to be bounded. All right. So, like, for example, the real numbers are not bounded because there's no number larger than infinity, or, I mean, like infinity and minus infinity here really are notations to indicate unboundedness in both directions. On the other hand, we do have these other things. So this is definition here. These are the intervals. An interval is a connected subset of real numbers. That means that if you were to look at the number line, and if you had a pencil that could draw forever, then these would be the sets that you get. Open intervals, half-open intervals, half-open intervals, closed intervals, and then you got your closed rays from infinity and from minus infinity to a, and of course also your open rays to infinity. The only thing that's missing from here, there's one interval that's missing from my notes, and this is kind of a dumb one, but it is technically an interval, which is the singleton. This is also an interval because it is connected and it is a subset of the reals. But that's the only one that's missing from my definition, although that is admittedly oh sorry, I was out of frame. This is also a interval, but it's the singleton, just 1 point. So you could draw that on a number line, boop, without lifting your pencil. So the closed, the open, sometimes this is called clopen, and sometimes this is called opposed intervals. These all have lower bound A, and they all have upper bound B, and minus infinity to A has a least upper bound A, but it's unbounded below. Likewise, A to infinity has greatest lower bound A, but is unbounded above. So I think all of this terminology is pretty natural, and you probably won't have much trouble with it as we use it. Now, so here maybe I should add some color. A to B, so like, you can use like a little open circle here, over to there. There's the open interval, if you want to picture it, I close the dot, and then do open as the clopen interval, and then why do I have this? Oh, it's closed. Both dots like this. You could draw this picture. Of course, there are other pictures you could draw, but those are some number line pictures we can use to illustrate the intervals, closed and open. Here's a fun question. So, you notice that we're using the notation in a somewhat ambiguous fashion. Well, see, think about 4-3. Is it, is that a pointer? Okay, this one's actually not ambiguous, right? 4-3, it cannot be an interval because 4 doesn't come before 3, right? So this has to be definitely a point. It's a point. All right. In contrast, if I had asked about 3-4, well, that would have begged the question: is 3-4, is that a point, or is it this? See, it could be this. It could be x such that 3 is less than x is less than 4, right? That's a possible interpretation of the 3-4 symbol. So it's just the nature of our notation. There is an ambiguity here, but context usually tells you whether we're talking about a point or an interval. If you're in doubt somehow, you can just ask me. I will tell you, most likely. Unless the whole point of the question is this example, in which case I might be kind of dodgy. Here's an illustration of the Cartesian product of the half-open interval -6 to 7 with 1, 5. Notice that the -6 for x is not included. See that dotted? It's dotted, whereas the other sides are solid because the other points are included in those intervals. All right, so you want to know how to create a rectangle? Cartesian product, that's how you do it. All right. So moving along here. So here's some fun facts about fields and such. Real numbers and rational numbers are examples of fields. A field is a set which satisfies axioms 1 through 9. In fact, both Q and R are ordered field. That means they follow axioms 1 through 10. However, the rational numbers, as I was mentioning, are not complete. They don't satisfy axiom 11. To be specific, pi is not a rational number, and the square root of 2 is not a rational number. But if you can take a subset of rational numbers, namely like truncated decimal expansions of the square root of 2, 1, 1.4, 1.41, and if you think about this set, the least upper bound of that set would be the square root of 2, and yet it's not in the rational numbers. That means that the rational numbers are not complete. All right. So there's like why it's not complete. It's missing some things. There's some holes in the rational numbers, and namely, it's missing the quote-unquote irrational numbers. So an irrational number is simply a real number which is not rational. So like, let me write it out here. Irrational. And I don't really have a number. I don't really have a symbol for that, but irrational numbers, what are they equal to? They're equal to the real numbers. Take away the rational numbers. Okay. So there's a good example of set difference. Irrational numbers are the real numbers which are not fractions of integers. Now, all right, anyway, moving on here. Here is some properties of inequalities that you may have forgotten, but we will use them. A squared is greater than or equal to 0, and a squared is equal to 0 if and only if a equal to 0. If and only if is a phrase that means you can go both ways, okay? Like, if I know this is true, then that's true, and if I know that's true, then this is true. That's what a if and only if statement is. It's also called a biconditional. We can add a constant across an inequality or subtract one. We can combine them. If A is less than B and C is less than D, then A plus C is less than B plus D. If we have, this is the transitive property for inequality, for less than, and the 5, you don't usually get into trouble with 5. If you've got a positive constant, you multiply by an inequality, it maintains the inequality, but this one will get you if you're not watching. If you have a negative number, you multiply an inequality, it flips it around, right? We go from less than to greater than, all right? And of course, these things are also true if you replace less than with greater than, or the less than or equal to or greater than or equal to as appropriate. Next up here, absolute value. Now, absolute value, I might be telling you something you didn't know. I don't know, but absolute value of a real number is denoted by this bar, x bar, and it's defined by the square root of x squared. Notice that the square root for us is the positive root. So by definition, this is non-negative. The square root of 0 is 0, and the square root of a number squared is the square root of a, it's a positive, square root of a positive number. So that's always real. In particular, this is the same as the following case-wise formula. Absolute value of x is x if x is greater than or equal to 0, and it's minus x if x is less than or equal to 0. And finally, we can also use the absolute value function to define distance between numbers. So the distance from a to b is defined by the absolute value of b minus a. All right, so like, for example, just throw an example in here. If I want to know what's the distance from like minus 13 to 7, right? I take the absolute value of 7 minus 13, and that gives me the absolute value of like 20, which of course is equal to 20, which is what we know. Like, there's 20 units between minus 13 and 7, because you got to go like minus 13 to get to 0, and then another 7 to get to 7, if we think about the journey from minus 13 to 7 on the number line, for example. So notice that the absolute value of x we can understand is the distance from the origin to x. And yeah, all right, I already talked about that. Here's properties of the absolute value function, which you may be less familiar with. These are important to us because we'll be studying the careful definition of the limit next week. And it's based on absolute value. All right, it's based on distance. The sentence is about distance. So to talk about distance, you have to talk about absolute value. And to analyze questions about distance, we need to know what are the rules for absolute value. And here they are. This is your toolbox, if you will. The things are go-to truths about absolute value that we should know. And we can use these and manipulate them. Manipulate expressions to our own will using these rules. All right, so it's non-negative. It's 0 if and only if it's the absolute value of a is 0 if and only if a is 0. This is very nice. The absolute value of a product is the product of the absolute values. That's a very, very important one to know about. This is a little bit sneaky. I don't know if you've thought about this before or not, but it's actually really important. The absolute value of a is less than epsilon. If and only if minus epsilon less than a less than epsilon. Now that makes perfect sense if you just think about it. So like basically if I was to draw the number line, you know, and like so here's epsilon minus epsilon, all right? And here's epsilon, and here's 0, right? And we've got absolute value of a. What is that? That's the distance from 0 to a, right? And this is saying that if the distance from 0 to a is less than epsilon, a has to be between minus epsilon and epsilon. Well, of course that's true, right? But notice what that thing does for you. It allows you to trade an expression involving absolute value, which is a case-wise defined thing, for this compound inequality, which is much more concrete in practice. But these are equivalent, all right? Now, on the other hand, if you've got absolute value greater than, that would mean that the distance from the origin to a is larger than epsilon units, right? So what that would say in terms of my number line picture up here is like you're over here or you're over there, right? So like that would be either a is less than minus epsilon. We do 2 lines there and we do some color, some coding, or you're greater than epsilon, like there. All right, so that also makes a lot of sense. And then you've got these so-called triangle inequalities. You know, a plus b is less than or equal to the absolute value of a plus absolute value of b, and here's one for the difference, and here's yet another one. Notice that this one is, whoa, oopsie doopsie. Huh. I'm not so, well, I'm a little fuzzy on this one. I need to think. I'm not 100% sold on this. This might be a typo, but I could be wrong also. All right, this one here, notice, is less than versus the other one is, you know, like the simplification is kind of different for this one and that one. Anyway, we'll use these and we'll come back and talk about them more. But all right, let's look at this in-class example. So I've got a is, what is it? Well, a is this set right here. I'm supposed to express a as an interval. All right. So if x is in a, then what is true? Then we have the absolute value of 3x plus 12 is less than 3. All right? But we just learned in part 4 of the theorem above that that's the same as minus 3 is less than 3x plus 12 is less than 3. And then we can use the properties of inequality, of less than that we already know. So subtract 12 across this, I get minus 15 is less than 3x is less than 3 minus 12, which is minus 9. And then dividing by 3, I get minus 5 is less than x is less than minus 3. Aha. So in other words, that means that A is actually equal to, apparently, -5 to -3. It's that open interval. And so there you go. I did part of the example here. We expressed A as an interval. And then we're supposed to do the same for B. B is a little bit different. I'll do it in a little different color. Use my handy dandy red marker here. So B is, what is B? So X is an element of B means the absolute value of 3x plus 12 is greater than or equal to 3. Okay. So that tells me either 3x plus 12 is less than or equal to -3, or 3x plus 12 is greater than or equal to 3. And then I solve these. So that gives me 3x is less than or equal to -15, or 3x is greater than or equal to -9. So x is less than or equal to -5, or x is greater than or equal to -3. So this says x is an element of -infinity to -5 inclusive, and this says that x is an element of -3 to infinity inclusive. So it's either in that interval or that interval, which means that in fact we have b is equal to -infinity, -5. All right, sorry, I'm out of frame. Union with -3 to infinity, right? And by the way, if you look at it, not surprisingly, the union of A and B is just what? What happens if you union that and that? Right? A union B is, in fact, everything, right? -infinity to infinity. Or as we like to denote it, simply the real numbers, by the way. I'm not sure my in-class example asked for that, but I thought it'd be nice to mention. So, yeah, there's that. Now, neighborhoods. What is a neighborhood? A neighborhood basically is, well, like a neighborhood. It's things that are a place that's close to you, you know? So an open neighborhood centered at A with radius, this number is a Greek symbol. That means delta. Delta. This is delta. Radius delta greater than 0 is denoted b sub delta of A, where b sub delta is all the real numbers that are within delta units of A. All right? And so that specifically is like this open interval A plus or minus delta. All right, so we go delta units to the left, we go delta units to the right of A. That's the ball of radius delta centered at A. You can also delete the center. So the deleted open neighborhood is like the delta neighborhood just without the A in the middle. So we just take the union A minus delta to A, and then union with A to A plus delta, where A is not included. So here's a picture of it. The ball is just this thing, not including the endpoints. It's open, and the deleted one also excludes the center. So like that. All right. Now the concept of a deleted neighborhood is going to be important to us when we study limits, because the limit is a thing where we study points close to the limit point, but not actually the limit point itself, so we delete the limit point. All right. All right, anyway, here's next in class example. We're supposed to find an A and a delta for which we have the ball of radius delta centered at A is equal to 311. And I've given us a hint. The midpoint of B delta of A is A. All right. And the length of the ball of radius delta is twice the radius. You could call it the diameter of the ball, if you like. All right, so what's the midpoint of 311? So midpoint, just to remind you, what you do is you take the numbers, you add them, and you divide by 2. And so that's 14 over 2, also known as 7. 7's the midpoint. And let's see here, the length of the length is what? Length of the interval would be like 11 minus 3, which would be 8. So that I said that's going to be twice the delta. So apparently we want to look at a ball of delta is equal to 4, ball of radius 4, centered at 7. All right, and let's just check our work. So that should be 7 minus 4, comma 7 plus 4. That's just going back to the definition right here. The ball of radius delta centered at A minus delta to A plus delta, right? Same as saying all the points within delta units of the center A. And yeah, there it is, 7 minus 4, 7 plus 4, also known as 3 and 11. So there you go. It's not hard. And of course, you can just conceptually piece that together. You don't have to use my midpoint formula. If you have an understanding of what distance means and you get this stuff, you could just write a number line and figure it out, you know. I think I said this already, but just to say it again, the connected subsets of real numbers are called intervals, and here's a complete list of the types. There's 9 types, I believe. All of the real numbers, oh yeah, the real numbers altogether, the rays, open or closed to infinity, and then you've got the, the closed interval, the opposed interval, the clopin interval, the open interval, and the singleton. So you got these 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 types of connected subsets of real numbers. Yeah. Now, this is a kind of clumsy definition of what I mean by connected, but it works for us, and so there you go. There are more sophisticated definitions of connected, but I am resisting those because I'm trying to keep these notes logically complete, but as technically simple as I can. All right. So this footnote has the more technical definition of connected if you're a math major and you're interested in that. In fact, that's part of a larger discussion which is called topology. Topology is the problem of defining which sets are open and which sets are closed, and more generally, what does it mean for a function to be continuous, which is just kind of a fancy way of studying whether functions sort of rip points apart or keep them glued together under their map, or do functions have sort of this adherence of points, or do functions tear points apart under their action? But topology is you could take a whole course in topology, but at the moment we just need the rudiments of topology as they pertain to this class, and there's just a few concepts we need. The one was the neighborhood. We talked about that already. The other is boundary point. And again, all of this is really more about language than anything else, so I just want you to know that there is a specific definition for boundary point, and here it's the definition. P, an element of U, a subset of the reals, is a boundary point if and only if every open neighborhood of P centered, every open neighborhood centered at P intersects points in the reals which are outside U and U. So it's a boundary point if whenever you take an open neighborhood around the point, you're getting points inside and outside the set. So you're straddling inside and outside. That makes it a boundary point. And we denote the boundary of U by BDU, or sometimes people will, well, let's just say, it's my notation, so boundary of U, all right. So you can also talk about right and left boundary points. It's a right boundary point if there exists an epsilon greater than 0 such that A minus epsilon to A is a subset of U, and likewise that. So let me see if I can picture that. So suppose that our set we're talking about is like, here's the A, right? And this is the set. Then to say that would be a left boundary point. So the point is A not inclusive to A plus epsilon. That right there, all those points in there that's a subset of U. All right, that makes it a left boundary point. On the other hand, now, see, the thing is, there could be holes, right? There could be holes. So we have to make epsilon small enough so that you don't have to worry about, like, this is a local idea. Like, if you made epsilon too big, you'd be outside of the set again, all right? On the other hand, right boundary point would be a picture more like this, all right? And the point is that, so this is the picture. Sorry, I'm drawing them opposite. This one's the left boundary point. This picture down here is the right one. So my bad. D-loop. D-loop. All right, anyway. So picture something like this. So we go from A to A minus epsilon. And that subset, that is a subset of the set in question. That makes it a right boundary point. Okay. In other words, if it's a left boundary point, all of the points just to the right of the boundary point are inside the set in question. If it's a left boundary point, all of the points just to the right of the given point are inside the set. If I just said that backwards, my apologies. I'm a little bit sleepy. I'd rather be telling you these things in person, but here we are. So anyway, for this example, if I have the open interval from 0 to 1, the boundary points of this are 0 and 1. Now 0 is not inside the set, but 1 is, all right? So it's possible for the whole set to be comprised of boundary points as well. For example, the boundary points of the natural numbers are the natural numbers. So any set of real numbers you can break down into two types of points. You got boundary points and you got interior points. For example, 0, 1 is the union of 0 with the open interval 0 to 1. 0 to 1 is the interior, and this 0 here is the boundary point. So the boundary of the set 0 to 1 it also includes 1, which is not inside the set, all right? So it looks like some sets include their boundary and some sets don't. I think we've got a definition coming up about that. An interior point means that you can find a ball around the point which is inside the set, and the set of all interior points is denoted int u. The interior points of the natural numbers, there are none, because any open interval around a natural number naturally includes non-natural numbers. The interior of 0 to 1 is 0, 1. All right, enough. So finally, definition, U is an open set, means that each point in U is interior, and it's a closed set if whenever you take the union of U with its boundary, you just get U again. In other words, a closed set is one which includes its boundary. Yeah. So I guess I'm supposed to give you an example at this point. Let's see here. Make sure I'm not missing something. All right. So that's probably, let me see if I can think of an example here. Let me take a gander over at your homework. What we got here? So I'll hopefully talk about these in class a bit more. All right, let's look at something. Let me do something kind of like problem 16. I did something kind of like problem 17 in the thing already. All right, so let's look at something. All right, let's let U equal to x in the reals, such that x is less than minus 8, or 10 is less than or equal to x is less than 13. All right. So that is actually, if we write it in interval notation, I'm sorry if I was out of frame, minus infinity to minus 8. Now that minus 8 is not included because that's a strict less than, unioned with this guy over here, which would be like 10 to 13. All right. Let me just draw a picture of this. So I'll make my number line just blue. All right, so here's my number line. Now let me draw the set in red. Well, maybe, I guess I'll draw it black. So -8, right? And then it just keeps going and going and going. Or over here you've got your 10, and then 13. Obviously not to scale, this is just a picture to visualize what's going on, okay? All right, so which of these points are interior points? Let me explain to you. If I pick a point here, right? So let's see here, that was, I forgot to label it, -8, right? So if I pick this point, for instance, -12, just for the sake of discussion, you see what I can do? I can easily go like, oh, from here to here, right? Like the ball of radius 1 centered at -12 is clearly a subset of U, right? That means that -12 is what's called an interior point, all right? If you can fit a little open neighborhood around the point, that makes it an interior point. So in short, the interior points, there's anything away from the boundary points, like that's an interior point, that's an interior point. There's infinitely many of them. So let me just get to the point here. Oh, I'm sorry, that's horrible. The interior points of U are -infinity all the way up to -8, as well as 10 not included to 13. Now, notice that 10 is not an interior point. See, because if you look at 10, let me use gray for a second here. If you look at 10, no matter how far you shrink like a little neighborhood around 10, you've always, no matter how small you make it, you've always got points over here to the left of 10 which are not inside your set. So 10 is not an element of the interior view. I guess that's an important thing to talk about. This is our symbol for not an element. We take the element symbol and put a slash through it. Means not an element of. All right, so how about boundary points? So boundary points, see, if you look at, well, I already did it for 10, but if you also look at like any open interval around -8, like here, or any open interval, little open interval around 13, there's necessarily points both inside and outside. Inside, outside, inside, outside. That means these are boundary points. And so the boundary points of U include, what do they include? You just got -8 and 10 and 13. And notice here, I'm not using intervals, I'm using curly bracket. Curly bracket is the notation we use when we have a finite set and we just need to make a list. See, there's a very big difference between this and that. 10, 13 with these parentheses, that's an infinite set. That's every single real number between 10 and 13, not inclusive. It's very different than that, all right? Yeah, so that's section 1.3. I guess I read it with you. I hope that helps you. And so next class, my intention is to I'm going to skip past the section on functions for the moment, and we're going to skip ahead to the section on algebra. We're going to do the algebra first, and then we're going to circle back and talk about functions after that. But I think the algebra is important, and so like what I'm saying is what we're going to do in class next is we're going to skip past this functions business for a bit, and we're going to skip ahead, skip, over here to section 1.6, which is on algebra, and I will talk to you about algebra, and we'll talk about how to complete the square and about how to factor and all that jazz, because many of you need a review, and that's fine. One of the things that calculus is going to do for you is it's going to make you much better at algebra than you ever dreamed of being in your algebra course. All right, so, and that's kind of generally the case in mathematics. If you want to get good at mathematics at one level, you need to do the next level above it. So, Anyway, hey, that's it. Sorry we couldn't meet in person, but it is what it is. Thanks, guys.